Okay, so in the last video we were looking at transverse type waves, where the wave moving energy from left to right makes particles vibrate up and down or vibrate perpendicular to the direction of energy transmission. And what we said was for transverse mechanical waves, you need really strong intermolecular forces to happen, so they only really happen in solids. This video is longitudinal waves. So these make particles vibrate in different directions to a transverse wave. And that's what we're going to focus on in this. And the other thing that a longitudinal wave does is it causes density variations in the medium that it's traveling through, like you can see on the diagram. So let's dive straight into longitudinal waves. First of all, some examples of these in reality. So a sound wave is a longitudinal type wave, and one of the types of seismic waves, the primary type, is also an example of a longitudinal wave. The P also sometimes stands for pressure or pressure wave. So how do we describe a longitudinal wave? Well, it makes the particles vibrate parallel to the direction of energy transmission. So if we look at our diagram here, showing us an example of a longitudinal wave, this is actually using a spring to send one along. You can see, so we have some names for sections. So you can see a section of very high density or high pressure is called a compression. A region of low pressure or low density is called rarefaction. And wavelength for a longitudinal wave marks the distance between compressions here. So in terms of going back to our description, this longitudinal wave is transmitting energy from left to right, and it's making the particles vibrate left and right, which is why we describe the vibrations as parallel to the direction of energy transmission. Okay. So we looked before at how effective transverse mechanical waves are at traveling. We can do the same thing with longitudinal waves as well. So just like transverse mechanical waves, longitudinal waves travel faster in a more densely packed, which usually goes hand in hand with strength of intermolecular forces. So longitudinal waves travel faster the more densely packed molecules are. And what that means is they travel fastest in solids and slowest in gases. And to give you some examples of the kind of speeds we're talking about, in a solid, sound can travel about 5 kilometers per second, whereas in a gas it can only go about 300 meters per second, and somewhere in between for liquids. And we do need to know these kind of approximate speeds of travel in the different liquids. So going back to our diagram, so this is actually showing a sound wave because we've got a speaker over here, which is causing some particles to vibrate, and those vibrations are then causing the longitudinal sound wave to form. So in terms of describing a sound wave, it's a longitudinal type wave that travels by particles colliding with one another to transmit the energy or transmit the information across. So as I said, the speaker vibrates the particles we can see on the left. They then collide with these other ones, setting up the sound wave. And in terms of how we actually produce one, it's essentially about causing particles to vibrate, and then those particles then need to collide with surrounding particles to start the sound wave traveling. And that's why they don't travel so well in gases. There are fewer particles for them to collide with, so the wave travels less effectively. So since we're talking about sound, that is something that obviously we can hear using our ears. The sound waves vibrate the parts of our inner ear, and that's what allows us to detect these sound waves. That's what our eardrum is for. So in terms of what we can hear, a typical human can hear from about 20 hertz. So that's describing a frequency. So 20 hertz all the way up to 20,000 hertz or 20 kilohertz. Different animals have different ranges. So that's something that varies. Another thing that varies is that as humans age, their ability to hear high frequencies decreases, and you can do this using a hearing test, which you may well do in lessons. So as I said, some different animals have different ranges. So a dog can go up to 45 kilohertz, which allows us to have some useful inventions. So we can make something called a dog whistle, which emits a frequency above the human hearing range, but inside the dog one, so we can whistle our dog without it annoying everyone else, which I think is kind of cool. Okay, so that's some sound waves. And we earlier quoted some speeds that sound waves travel at. We said it was about 300 meters per second in air. So what we're going to take a look at now is how we can actually go about measuring that. Where's that value come from? And what we need is essentially something to produce a sound, something to produce an echo, so something to reflect sound waves back, and a timing device. And if we use long enough distances, we can measure the speed of sound. So what we do is, as I said, we use echoes. So that's why we need this wall you can see on the diagram, because we need an echo to be produced. And what we're going to do is measure the time between emitting a sound wave and hearing its echo. And we also need to measure the distance the sound wave has traveled. So on the diagram, we can see we've made it a nice easy distance. The sound wave is going to travel 200 meters between being emitted, being reflected, and then coming back to you. And once we've measured the distance, once we measured the time, we can work out what the average speed is. And the reason we use such a long distance is, if we use a short distance, the time between emitting the sound and hearing the reflection will be very, very small, which will make it an inaccurate measurement. If we have a large distance, we get a larger time, so generally we can measure it more accurately. And then the way we'd go about doing it, average speed is distance over time. The distance traveled by the wave is 200 meters. The time we've got on a stopwatch, and it should come out as about 300 meters per second. It does vary slightly with temperature and air pressure and all these other things, but it will be around 300. Okay. So another type of longitudinal wave, which again is actually technically a sound wave as well, is sonar. And this is something that initially anyway animals can use, so something like a dolphin, something like a whale, bats also make use of this. Humans then also learn to use it, which is how submarines are able to locate, and boats and things are able to locate things in water. So first of all, what does sonar stand for? So sonar is sound navigation ranging. So you can see the S, O, N, A, and R are taken from the start of those words. And essentially what it means is using sound waves to locate things and find their range. So in terms of how this works, it works in a very similar way to the experiment that we just saw. It works based on echoes. So essentially what you do is you measure the time between emitting a sound and receiving an echo. And if you know the speed of the sound in the material, you can therefore work out the distance the object is away. Well, actually, you calculate the distance to the object and back, and then so you've measured twice the distance to the object. So animals are obviously not measuring time, and they don't know what the speed of sound in water is, but their brains have learned to essentially interpret what a signal means in terms of how far away that object is. But in submarines, this is exactly what's happening. They are measuring the time and using the speed of sound in that particular material, and they use that to find the distance. So that's how sonar in submarines and animals kind of works. Also use a different kind of sound wave called ultrasound. So what ultrasound means is it's above the human hearing range. So in terms of how ultrasound works, essentially what you're trying to do is find the depth of an object. Usually we use ultrasound to look inside humans, especially if we want to look at a fetus that's growing. And what we want to know is essentially how far away the object is. So it's the same process. Again, with reflecting sound waves, this time we're using particularly high frequency ones. So you use the same emission echo system to find the distance of an object. And we can see we have an object we call a transducer. So that turns an electrical signal into vibration, which then produces sound waves. And then what we do is we can get a measure of the density of the thing that we're looking at. So if you measure the percentage of waves that get reflected, that tells you about the density of the material the waves are reflecting from. And you get an output like you can see over here. So you'll get, these are the first waves that have been reflected and come back, and we see we've got a particularly low percentage here. So that might be just being reflected off the skin or something along those lines. So that's what we've got here. Then we've got these ones here where we see they're being reflected off the baby. Baby's density is going to be different, and so we get a different percentage reflected there. So those are the things we're measuring. We're measuring the distance the object is away, and we found a way of measuring the density of the object as well. And what we do is we take lots of these measurements. So we move the scanner around and take lots of these measurements, and a computer then takes all that data and builds an image, and that's what you can see on a screen. And we're now able to do them in 3D, which is quite impressive these days. Okay. So the last kind of mechanical wave to have a look at, and that brings the two types of wave together, the transverse and the longitudinal, are seismic waves. So when an earthquake occurs, it produces two types of waves. It produces a longitudinal, sometimes known as a pressure wave, hence why it's called a P wave. It's also sometimes known as a primary wave because they travel faster. And it also produces what we call a shear wave, sometimes also known as a secondary wave, which is a transverse wave. So earthquakes produce these two things. So let's firstly get our descriptions down. So our P wave, our primary or our compression or pressure wave, are longitudinal and travel the fastest. S waves or secondary or shear waves are transverse and travel the slowest. And they also cannot travel through the core of the planet, whereas the primary or P waves can travel through the core. And that's one of the ways we actually know that there is a liquid core inside the Earth, because at some places we only measure P waves, we don't measure S waves, and that tells us the wave has had to go through the core. So those are our two types of seismic wave produced by earthquakes and volcanic events and stuff. So in terms of actually locating the epicenter of an earthquake, what we essentially do is we measure the difference in time between P waves and S waves arriving. And because we know the speed at which each of those waves travel, we can therefore locate where, or at least know the distance the earthquake's epicenter is away from us. So what you're seeing on this diagram are three locations we are taking measurements in. So let's say we're in Minneapolis, we measure the time difference. That allows us to know how far away the epicenter is, but it doesn't allow us to know where the epicenter is. All we know is the epicenter is somewhere on the perimeter of that circle. And we do the same thing in Detroit, and we do the same thing in Charleston. So we've got three measurements and three circles. So we use a process called triangulation, so essentially using three sets of data. If we find the intersection of their three circles, we can find precisely where the epicenter of our earthquake is. Okay, so that's how we locate earthquakes. So just to give you an example of this in action, so you see how it works. So let's say P waves travel at 8 kilometers per second in the Earth's crust, S waves travel at 4 kilometers per second, and we know they travel slower, so that kind of makes sense. And let's say we measure this time, or these times of arrival. Now, we don't know the time which the earthquakes were emitted. We just know when we detected P waves and when we detected S waves about 23 seconds later. So some things that we're going to use. So first of all, we know the difference in time is 23 seconds. And we know that the distance the primary waves have travelled is the same as the distance the secondary waves have travelled, because they both come from the same place to the same place. So what we can do is use our average speed equation to go, okay, so if we know the distance the primary waves have travelled, we essentially know the speed times the time, the distance the primary waves have travelled. And the same thing for the secondary ones there. So we're just using speed equals distance over time here and rearranging it. Then what we can do is go, okay, well, we don't know what the primary time is, and we don't know what the secondary time is, but we know the secondary time is 23 seconds longer than the primary time. So I've made a substitution in our equation there. Then what we can do is multiply out those brackets. So essentially I've multiplied Vs by Tp and Vs by 23. Then what I'm going to do is I'm going to collect all of the Tp terms on the left-hand side. So I subtracted VSTP from both sides. And then what I've done is I've factorized that. So you see both things have a factor of Tp on this side. So I factorized that out. And we've got Vp minus Vs. And then what we can do is then calculate what the time for the primary wave is, because we know the speeds at which they travel in the material, because we can substitute those in, and we find that actually the primary wave took 23 seconds to travel from the epicenter to our location, and then it therefore took 46 seconds for the secondary wave to arrive there. So once we know that time, we can then calculate the distance using the speed, and we find out the earthquake's epicenter is 184 kilometers away. So that's actually how the calculations go. That's a bit advanced beyond what you need to know about seismic waves, but I thought it's useful to actually see how that works in action.